Okay, let's dive into this. Welcome to the Explainer. So, today we're taking a look at something absolutely foundational, the underlying logic of set theory and its operations. Now, I know that sounds like a mouthful of abstract math, but honestly, it's the absolute bedrock of how we logically organize, well, pretty much everything. We're going to unpack exactly how these mathematical rules are secretly governing the world around us. Let's get into it. It brings up a huge question. How do we organize everything? It's a massive concept, right? But think about it for a second. We are all just instinctive sorters. We naturally group our clothes by season, we organize our phone apps by what they do, we even sort the people we know into different social circles. We categorize things just to make sense of a really chaotic universe. And set theory? It's really just the formal mathematical version of that exact same human instinct. So let's actually formalize it. By definition, a set is simply a collection of distinct elements. That's literally it. I know. It sounds incredibly simple, and honestly, it genuinely is. You can have a set of numbers, a set of primary colors, or, I don't know, a set of your favorite vintage coffee mugs. By grounding this abstract math in the super relatable idea of just collecting unique items, we've got our perfect starting point.
Moving right along to Section 1, meet the set operations. This is our logical toolkit. Okay, so now that we've got our collections defined, what do we actually do with them? Well, we apply operations. These are dynamic actions that filter and combine our data. And we've got 4 fundamental tools here: union, intersection, difference, and complement. Just take a look at the symbols. You've got the U shape for union, the upside down U for intersection, a standard minus sign for difference, and that little prime mark for complement. These definitely aren't just dry textbook terms. They've got a mathematical rhythm to them that lets us manipulate literally any data in existence. Now, what's really interesting about this slide is how we can translate these math symbols right into plain English. Let's start with our first 2 filters. Union, which is written as A union B, simply means taking all the elements in set A, or in set B, or in both. It's basically a massive OR filter. You're just lumping it all into one big bucket. Intersection, on the other hand, is way more strict. Written as A intersect B, it's an AND filter. You are only keeping the specific elements that those 2 sets share in common. Continuing on with our toolkit, we have difference, noted as A minus B, and this one is exactly what it sounds like. It captures the elements that are in set A, but specifically not in set B. So think of it like this. If A is all the fruits in your kitchen and B is all the red things, A minus B strips away all the red fruits and you're just left with bananas and green apples. Simple, right? Then we've got the complement, written as A prime. It simply asks, what is not in set A? It's all about capturing the negative space. So if your universal set is everyone you know, the complement of your x's is, well, literally everyone else that's left over. All right, Section 2, the rules of the game. Let's look at the properties of sets. Because listen, every good toolkit needs an operating manual, right? The laws of physics that keep our logic from just totally breaking down. Here, we rely on commutative, associative, and distributive laws. And yeah, I know, that terminology sounds super intimidating and dense, but the reality is actually beautifully simple. Commutative just means the order doesn't matter. A union B is the exact same thing as B union A. Associative means how you group things together isn't going to change your final outcome. And distributive, that just dictates how these operations mix smoothly together. Really, it's just common sense structural integrity for our data. Let's move to Section 3 and see how this builds. Visualizing with Venn diagrams. Now, if you're a visual learner like me, seeing letters and math symbols is fine, but it's when you see a picture that the light bulb actually turns on. Enter the Venn diagram. This is our ultimate visual cheat code. John Venn introduced these way back in the 1880s to teach basic logic, and they brilliantly illustrate all those mathematical properties we literally just went through. So instead of doing all the heavy mental lifting of algebra to remember what A intersect B means, you just look at 2 overlapping circles and highlight that middle section. It's immediate, it's elegant, and it maps the abstract math directly to your visual cortex. Which brings us to our final, and honestly, probably our most fascinating thought here. Are these simple operations secretly running your digital world? Because every single time you type a query into a search engine, you are actively utilizing set theory. Think about it. Searching for shoes and sneakers, that's an intersection. Searching for shoes minus boots, that's a difference operation. These exact tools, union, intersection, difference, and complement, are the invisible logic engines quietly operating behind almost every single algorithm today. Pretty amazing for a totally simple collection of distinct elements, right? Thank you so much for joining me for this explainer, and keep asking those big questions.